For years, cosmologists hoped this was a technical problem, a calibration issue, a data processing issue, a subtle measurement mismatch that would shrink away once the instruments got better. Then the instruments got better, and the problem stayed. That is why one of the most important stories in astronomy right now is not a new planet or a dramatic image. It is a measurement that refuses to fit the universe we thought we understood. The issue sounds abstract at first. It is usually called the tension around the expansion rate of the universe. But here is the simple version. When scientists use one set of methods to estimate how fast the universe is expanding today, they get one answer. When they infer that expansion rate from the early universe using the standard cosmological model, they get another. Those answers are close enough that casual viewers can miss the drama. They are also far enough apart that cosmologists cannot comfortably ignore them. That is the whole emotional engine of this story. Not chaos, not collapse. Discomfort. And in real science, discomfort is often where the important work begins. The public usually encounters this kind of story in a distorted form. Either everything is fine and the discrepancy is boring, or everything we know is wrong and the universe has basically broken. Neither version is accurate. The real story is better than that. A mature scientific model is under pressure from improved observation, and the pressure has not gone away. That is where Webb enters the frame. Webb was never just a prettier camera. It was built to reduce ambiguity, to resolve detail, to sharpen measurements, to help astronomers distinguish between messy data and incomplete theory. That is why Webb matters here. If a disagreement persists after better measurement, the conversation changes. The problem stops looking like pure observational sloppiness and starts looking more like a model problem, or at least a model stress problem. That does not mean the standard picture of cosmology has failed. It means parts of it may not be as settled as they once felt. To understand why that matters, you need to understand what the measurement stands in for. This is not just a number floating in a textbook. The expansion rate acts like a conversion factor across the entire cosmic story. It affects how we connect distant light to time, how we connect distance to structure growth, how we connect the early universe to the one we see now. If that factor is wrong or incomplete in some important way, the consequences do not stay local. They spread. That is why one stubborn measurement can matter so much. It is not powerful because it is dramatic by itself. It is powerful because it sits in the plumbing of the model. Change the plumbing, and a lot of familiar rooms start looking different. The local side of the story is often explained through distance ladders. Astronomers use one class of object to calibrate another, moving from nearby well-understood measurements outward to much greater distances. The farther out the ladder goes, the more the uncertainties have to be controlled carefully. That is why calibration became such a central word in this debate. Calibration is the polite face of fragility. It is where tiny mismatches can become big consequences if not understood. On the other side of the equation, astronomers use information from the early universe inside the standard cosmological framework to infer what the present-day expansion rate should be. That route does not start from the local ladder. It starts from a model of how the universe evolved from its earlier state into the one around us now. If those two routes disagree persistently, something has to give. Maybe one of the methods still hides residual systematics. Maybe the calibrations are not quite as secure as we think. Maybe the framework that links early conditions to the present is missing a term, a transition, or a piece of physics that matters more than expected. That uncertainty is exactly why the story is so compelling. It does not resolve cleanly into one villain. Instead, it forces science to keep interrogating itself. And that is where Webb became so important. Webb could not solve the entire problem by itself, but it could reduce one of the easiest escape routes. The hope was that better resolution and cleaner observations would show that some part of the local measurement chain had been biased by instrumental limitations. In other words, Webb had the power to make the whole issue look smaller. Instead, the broad problem remained. That does not automatically elevate every speculative explanation. It simply makes the tension harder to dismiss as wishful overinterpretation. This is why the phrase "under tension" matters so much. It sounds mild, but in scientific language, it often means the framework is still functioning while carrying a growing amount of strain. The model still works in many ways. It still predicts and explains an enormous amount. But a specific region of parameter space refuses to feel comfortable. That is not the same thing as catastrophe. It is more like structural creaking. Most viewers do not find that emotionally satisfying at first, because it lacks the clean release of a solved mystery. But the creak is where the real action lives. The history of science is full of moments when the biggest breakthroughs did not begin with a total collapse. They began with a model that still mostly worked, and one measurement that would not quite behave. That is why this story matters beyond cosmology enthusiasts. It shows how frontier science actually moves, not in cinematic bursts of instant replacement, in zones of discomfort where observation gets good enough to make old confidence feel too smooth. There is also a reason this topic performs well on channels like the one you are modeling. It combines three things audiences love: scale, legitimacy, and controlled instability. The scale is obvious. We are talking about the expansion history of the universe. The legitimacy comes from the institutions and instruments involved. This is not fringe material. It is core astronomy. And the controlled instability is the hook. A trusted framework is not collapsing, but it is being forced to answer harder questions than before. That creates the perfect kind of curiosity. Not fake forbidden knowledge. Real pressure inside an accepted system. This is also why restraint matters. There are several bad versions of this video that would probably get clicks and still weaken the channel. The worst version says the universe is broken. Another version says scientists hid the truth. Another version says one instrument has disproved everything. All of those framings are weak because they burn trust for short-term drama. The stronger framing is more disciplined. One measurement is still resisting a clean fit. Better observations have not erased the disagreement. And that means the most successful cosmological model in use today may still be incomplete in some important way. That is already a huge story. You do not need to overcook it. In fact, overcooking it makes the story less impressive. Because the real power of this topic is that the tension survives responsible scrutiny. It is not just loud on the internet. It exists after serious observation, careful analysis, and repeated attempts to reduce or explain it. And that survival is what changes the tone. If the disagreement had vanished, this would have become a footnote about the self-correcting nature of measurement. Because it persists, it becomes something more valuable. A live fault line in a mature field. That also explains why Webb is such a good symbol for the story. Webb represents improved vision. And improved vision did not make the discomfort disappear. It clarified where the discomfort actually lives. That is a subtle but important difference. Sometimes better tools solve mysteries. Sometimes they stabilize them. They remove bad explanations and leave the hard explanation standing alone. That is what makes this particular measurement feel so durable. The easy ways out keep looking less easy. That does not tell us what the final answer is, but it tells us where not to look for comfort. This is where the stakes widen. If the tension eventually points to some revision in the model, the implications could reach into multiple parts of cosmology. Expansion history, dark energy behavior, structure formation expectations, how confidently astronomers translate remote observations into age and growth narratives. Even if the eventual change is mathematically modest, the conceptual impact could still be large. Because cosmology is a connected story. And when connected stories adjust, they rarely adjust in only one sentence. That is why the phrase missing ingredient keeps showing up around this topic. A missing ingredient is not a theatrical phrase. It is a scientific one. It means the current recipe produces a lot of accurate output, but may still leave a persistent residual that will not dissolve. In practice, that is often how real revision begins. Not by throwing away the recipe, by realizing one ingredient was fixed when it should have been dynamic, or omitted when it should have been included. This is also a useful reminder that uncertainty is not a weakness in science. Uncertainty is one of science's most valuable instruments when it is handled correctly. A field that notices tension and works on it is healthier than a field that buries it under slogans. That is why this story is not a sign of failure. It is a sign that cosmology is still alive enough to be unsettled by evidence. And evidence is supposed to be unsettling when models get too comfortable. There is also a deeper strategic reason this measurement matters so much. Astronomy cannot run controlled experiments on the universe itself. It has to read the cosmos through light, calibration chains, statistical interpretation, and the frameworks that connect one era of cosmic history to another. That means any durable mismatch between observation and framework is especially important. It is not just a disagreement about bookkeeping. It is a disagreement about translation. How reliably can we translate measured light into a confident story about the universe? How much trust belongs to the latter? How much trust belongs to the model? And which assumptions feel safe only because they have been comfortable for a long time? That is why this topic keeps surviving simplification. The public wants a single villain: bad telescope, bad calibration, bad theory. Real science keeps discovering that the more interesting possibility is stress inside the handshake between data and theory itself. And when that handshake stops feeling effortless, a field either improves the data, improves the framework, or eventually improves both. That is what makes this such a strong frontier story. Not that the universe suddenly became unknowable. That precision is now good enough to expose exactly where certainty becomes expensive. The public often says it wants scientific truth. What it usually wants is scientific closure. Those are not the same thing. Truth at the frontier often arrives first as pressure, then as method, and only later as closure. Right now, this story is still in the pressure phase. And that is exactly why it deserves attention. Because if you only pay attention after closure, you miss the most interesting part. You miss the moment when improved observation exposes the precise place where human understanding is no longer smooth. That is what this measurement is doing. It is not destroying cosmology. It is revealing the cost of pretending cosmology is finished. That is the real Webb story here. Not just that the telescope sees farther, that it helps force a more honest conversation about what our best model still struggles to absorb. And that edge, the place where the fit stops feeling easy, is where the next real leap usually begins. If you want space explained by consequence, subscribe. The next briefing is about the brain problem that could stop deep space travel long before propulsion does.